This introductory lesson to kick off our second unit is going to introduce the concept of limits, and then we're going to take that concept and determine limits by looking at graphs. So I'm going to start by introducing you to some notation. So when you read this, you see this LIM, and then under it X with an arrow, and then 1 with like a plus sign in the exponent area. So how you're going to read this is the limit as X approaches, okay, and actually all of them are going to start with the limit as X approaches, so I'm going to leave that up top here. And then for this one, it's the limit as X approaches X equals 1 from the right. Okay, this is the limit as X approaches X equals 1 from the left. So you can see this positive sign would mean we're approaching from the positive side, aka the right, and this negative sign would mean we're approaching from the negative side, aka from the left. And then if there's neither a plus or a minus sign up in that exponent, then that's going to be the limit as X approaches X equals 1 from both sides simultaneously. So you're going to want to have that notation down. I would recommend writing it down so it sticks. New notation, new concept for us. But what does this mean really when we say from the right, from the left, from both sides? It would help to have an example. So another way of thinking about this is, what does the output, and we should say what is the output f of x approach as the input x approaches 1 from the right and from the left? That is what this notation is really asking. What does the output f of x approach as the input x approaches 1 from the right and from the left? So you can pause to get that copied down, and then we're going to look at an example here. So here's a nice crazy piecewise graph, and we're going to find the limit as x approaches 1 from the right, 1 from the left, and from both sides. So we're going to go to x equals 1, which here's 0, so this must be x equals 1 right here. And then this would be x equals 2. So what I'm going to do is I'm going to go up to my graph, and I'm going to approach x equals 1 from the right-hand side. So here's x equals 1. I want to approach it from this side, but I want to do that along the graph. So as I approach x equals 1 from the right, what do I seem to be approaching? It seems like I'm approaching y equals 5. So I'm going to say that this is equal to 5. Okay, what about if I approach x equals 1 from the left-hand side? So here's x equals 1. I'm going to approach it on the graph from the left-hand side. And yeah, I'm still approaching 5. And since I approach the same thing from both the right and the left, then the limit as x approaches 1 from both sides is just going to be equal to 5. And this was a silly example that's not always going to be the case, but because we're just at a nice normal point here, then our limit just ends up being whatever the output is. So let's look at another one. The limit as x approaches negative 4 from the right. So here's negative 4. If we go along our graph and approach it from the right, it seems like we're approaching. So that's actually y equals 0.5, because that's y equals 1, right? Y equals 1, y equals 2, so right here is y equals 0.5. So we'll say this is equal to 0.5. Okay, I think we can see that from the left we're also going to approach the same thing. We're just going to approach 0.5. And then once again, because we're approaching the same thing from both sides, the limit as x approaches negative 4 from both sides is just going to be equal to 0.5. So the limit is just the output, the y value, right? Like that's what it seems like from our two examples so far, right? As x approaches 1, we were just approaching 5. As x approaches negative 4, we were just approaching 0.5. So is that what this is? If so, why do we even have this concept, right? Why do we even consider left and right limits if it seems like, well, they're the same, right? Well, I think we can look at points on this graph where the left and the right limit are not the same, and that's where we're going to be more focused, okay? So the limits are most useful at holes where the graph has no output. So for example, if I have a nice curve that has a hole right there, okay, there's no output there. So I can't just plug in, let's say this is x equals 1, 2, 3, right? F of 3 is undefined because there's no output there. So I need to be able to apply a limit, right? F of 3 is undefined, but I can do the limit as x approaches 3. That is defined. So it allows me to talk about a graph even if it has a point where there is a place where it's undefined. Right? That's what a limit is going to help me do. It also helps me talk about graphs when there's a piecewise break. So if I have something like this, which happens sometimes in graphs, and let's say this is at x equals 2, okay? Well, then we can look at the limit as x approaches 2 from the left, which is going to be different from the limit as x approaches 2 from the right. And it turns out that if we're approaching two different things from the left and the right, then the limit by definition does not exist. Okay, so the limit as x approaches 2 from both sides here, we would just say DNE does not exist because the limit as x approaches 2 from the left is not the same as the limit as x approaches 2 from the right. There's a break in the graph. Okay. So we'll do a couple examples where that happens. Here's the limit as x approaches 5 from, negative 5, which is right here, from the left, the right, and from both sides. So as we approach negative 5 from the left, it seems like we're approaching y equals 1. So this is going to be equal to 1. It seems like we're also approaching 1 from the other side. So the limit as x approaches negative 5 is equal to 1. But because there's a hole at x equals negative 5, we would say f of negative 5 is undefined. There's no output there. There's just a limit. Okay. Now if we go to x equals 2, say if we do 2 from the right, again, we're going to approach from the right-hand side. We're going to go to our graph. As we approach 2 from the right, it seems like we're approaching 1. As we go to from 2 to the left, so we go to our graph, approach x equals 2 from the left, we're approaching y equals 2. So then the limit as x approaches 2, we're going to say does not exist because these two limits are not equal to each other. The right and the left limit are not equal to each other. And then finally, we're also going to say that the function itself at 2, f of 2, is just going to be equal to 1 because that's where we have a filled in point right here. Okay, so f of 2 is equal to 1. 2 from the right is equal to 1. 2 from the left is equal to 2. The limit as x approaches 2 does not exist. And f of 2, the function itself, is just equal to wherever the point is, okay, which is at 1. Okay, one more example. Let's do the limit as x approaches 3 from the right. You can pause this if you want to try to do it by yourself, or you can just watch me. So let's go to x equals 3. 1, 2, 3. So we approach 3 from the right. It seems like we're approaching negative 1, right? Negative 1, 2, 3, 4, 5. So yeah, that's negative 1. Okay, what about 5 from the left? So here's x equals 5. Let's approach from the... I messed up 3 from the right. I accidentally did 3 from the left, so let's try that again. Okay, 3 from the right is going to be... Oh, no. Oh my gosh, I got so messed up. I was looking at this, so let's fix that again. 3 from the right is equal to negative 1. I was suddenly looking at x equals negative 1. Okay, so yeah, 3 from the right is equal to negative 1. 5 from the left, so here's x equals 5. We're going to approach from the left, and that seems to be, also, that's equal to positive 1. Okay, because we're approaching positive 1. But then if we do the limit as x approaches 5 from both sides, which is what this is asking, from the left and from the right, we're approaching different things, so that's going to be does not exist. Okay, so that's it, and now you have a little bit of extra practice to work on through Desmos.